Thank you for joining us today for our second in the AASHTO Reuniversity web series, Proficiency Sample Reports Explained. I'm Kim Swanson, and I'm the Communications Manager at AASHTO Resource, and I'll be acting as a moderator today. Today, we're joined by John Molesky, the AASHTO Resource Proficiency Sample Program Manager, and Ryan LeQuay, the AASHTO Resource Laboratory and Testing Manager. Ryan will be here to help me sift through the questions and potentially answer some of them for us. But for now, I'll hand it over to John. Thank you for being here today, John. Take it away.
Thank you, Kim. I appreciate it. Thanks to all of you for joining. I'm glad to see that there are so many people who are interested in gaining a little bit more information about the Proficiency Sample Program and the reports. And without hesitation, I'm going to get into it. I think everybody is very interested in trying to learn more about the program and take care of those answers to those burning questions that they have. So I think we're going to go ahead and we're going to get started. There we go. I think we got it now. All right, so moving into it, we're going to take a look at these learning objectives. We're going to look at the general program Q&A, review the calculations for the z-scores. Also going to do things like locate other information on the AASHTO resource website. And we're also going to identify and discuss data, the distributions and analysis, and understand the components of the Uden plot and of the performance charts. So just to kind of give everyone a little bit of information on this session is going to be similar to the one that we offer at the technical exchange. So if you've been through it, hopefully it's a good refresher for you. And we're also going to take out a little bit of the content in that presentation to make sure that we have appropriate time to answer all those burning questions that are out there. So with that in mind, we're going to move along, and like I said, there'll be opportunity for us to stop and answer the questions that you all have posted in the chat box. So moving on beyond our learning objectives. Accessing the data on the AASHTO resource website is going to be our first topic. So basically, you're just going to log in under your laboratory's criteria and credentials, just as you would for anything else, for resolving deficiencies from an assessment, or just looking for general information, basically the same criteria. And to specifically get to your data, once you log in and you are in your portal page, you can scroll down toward the bottom and you'll see the link that's listed there. It's a radio button that says View PSP Ratings. So that'll take you directly to the drop-down page where you will have the opportunity to select any of the sample programs that are in our scheme. If you are in any of the programs, what will happen is you'll be able to move on to the next window. However, if you are not in a specific program, you'll receive a message saying that you're not able to do so. So please keep in mind, this is only going to have functionality for program schemes that you are enrolled in. So once you make that selection for your dropdown and the specific sample type that you're looking for, you're going to see the compilation of the rounds for every round that you've participated in. In this example we have here, you can see roughly 6 rounds of viscosity graded asphalt. If you are a long-standing participant in the program, you may see 20 to 25 rounds of data. There's usually quite a bit of information for you to look at, and that's the intent of the program. The program is designed to be a continual improvement process, and you have the capability to ensure consistent results over the course of time. And that's one of the most valuable things that we can offer, is that measure of consistency. If you're a new laboratory getting into the program, then you may only have 1 or 2 sample rounds. However, we're going to work with you to make sure you build that knowledge base and make sure that you have a good and thorough understanding of the entire process and what you're doing for your control capabilities. Moving on to the rating sheet. So this is a generalized rating sheet that you'll see for each one of the samples that you've submitted data for and the final reports have been released for. You can see that there are a few different columns that we have in here. We'll highlight them in the next slide. And you can see we have the sample rounds. In this specific example, it's sample 43 and 44 from a gyratory sample. The sample tested the test was for the rice sample. So we're looking at things like the lab data, the z-scores, the grand averages, and obviously what you really, really want to focus on are the ratings. That's, kind of the big thing that everybody wants to look at. You want to make sure that you're viewing the appropriate data and looking at the exact information that you want to look at. And like I said, the biggest thing that everybody comes to look at when we come to these pages are the ratings. Did I score well? How well am I doing compared to everybody else? So that's exactly what we're looking for. So we're already at a stopping point. Like I said, I wanted to try to build quite a bit of time in this to make sure that we could address as many of the questions as possible from our participants in this session. So Kim and Ryan, do we have anything in the chat box at this moment?
Not at this moment, John. There's no questions, which I am surprised about.
Perfect. That means I'm either doing really well and really clear, or I've already put people to sleep and it's only about 4 minutes into the presentation. So hopefully the questions will come as we move a little bit further along. So we'll see. So the next section, if there are no additional questions.
We just got one.
All right.
Yes.
Okay, here we go.
Cash wants to know, can you explain the difference between a positive and negative rating?
Absolutely. So we're actually going to touch on that a little bit in the next section, which is a great segue. But all that symbol means, whether it's a plus or a minus, it just means the side of the average that you fell on. So if it's a positive number, then your data was above the average. If your data shows a minus sign, or your rating shows a minus sign, then you simply fell on the lower side of the average. It has no connotation with either being a good or bad rating. It's just an indicator of where your data fell as relationship to the average.
Well, I thank you for that. That was what he wanted to know. So thank you. And we have another question, and I think you're going to get to it. But it was, how is the lab rating determined in the last column? I think you're going to get to this coming up. But
yeah, we're going to go into that in a little bit more detail. So I think we can hold off on answering that one, and I think the presentation will take care of that itself. So if there are no other questions about just general access with data or anything on the AASHTO resource website, we'll move in and we'll go right to that next section. All right, perfect. Here we go. So distribution of the data and calculation of ratings. So like I said, this is going to be our next focus for this section, and hopefully this will address some of those questions that are out there. So the first slide we're going to look at is we're going to talk about rating versus location in the distribution. So here we have our standard bell curve, right? Normal distribution. It looks pretty good. And you can see how we have the lines, or the z-scores and ratings kind of shown there on the graph. So when the peak of the graph would obviously be the grand average. That's the quote unquote the perfect score, or the perfect data point, I guess I should say. And just to reiterate that our data is a consensus value. So we determine that average and the standard deviation based on the data that all of you submit. It does not have anything to do with one expert laboratory. Ryan's an incredibly good laboratory technician. He's a great manager. But we don't feel that we should be setting our results as the quote unquote correct score. We're going to allow all of you to decide what that correct score is based off of our statistics and the grand average that was provided by all of you. But what you can see here, as you move further away in the distribution, each standard deviation or portion of a standard deviation causes a lower rating. So what we're looking for is 5s and 4s, and each I guess how the way to say it is that the first standard deviation is a rating of a 5, so within 1 standard deviations. Each half standard deviation beyond that will result in 1 lower score unit. So if you're inside of 1 standard deviation, you're going to get a 5. If you're between 1.001 and 1.499999 all the way till infinity and beyond, you would receive a 4. So that's the way that the rating system works. And I kind of touched on this a little bit. Good ratings are typically a plus or minus 3, 4, and 5. A plus or minus 2 is generally an action signal. It's, this is where you would want to start doing some corrective action investigation. The accreditation program requires, I guess it's actually AASHTO R18, requires that any low rating beyond a 2 would result in a corrective action that needs to be documented by your laboratory for conformance to that quality standard. So once you start hitting that 2, that's where you need to do some investigation. And then we would consider a poor rating anything that is a 0 or a 1. At that point, more than likely that is some sort of a major deviation that took place. Not all the time, but for the most part, that's something that's pretty far out there. So then one of the other common questions we get is, what percentage of laboratories receive quote unquote good ratings? Or, the other side of it, well, how many labs get bad ratings? We see that, hey, you suspended so many laboratories. This is so, hard. This is so crazy. So we, just looking at normal statistics, it is the 68, 95, 99 rule. And what that simply means is, we have our good old normal distribution, our bell curve there with our ratings on it. So the first standard deviation incurs about 68% of the data. So I want to make it clear, though, that this 68% of the data is the core data that we use in our analysis. So at some point, we're going to probably go into a little bit of a deeper dive with one of these presentations on how the actual proficiency sample program analysis works, to go into the whole process of removing invalid data, unpaired data, and what we also consider outlying data, till we get to what we consider is the core data. And by core data, we're saying that that's the best, the most accurate data that we can use for the statistics. So when we talk about this 68, 95, 99 rule, that's based on the bounds of the core data that are selected for the analysis. So that first standard deviation includes 68% of that data. The second standard deviation includes 95%. That's typical confidence limits, confidence intervals for standard statistics. We want to see everybody inside of 95%. And that's where you see that transition between a 3 and a 2. That's essentially the cutoff. And then once you go out towards 3 standard deviations, that 3 standard deviation bound is approximately 99.7% of the data. So within that core data set that we select, 99.7% of that data should be included in that analysis. So once again, if you're beyond 3 standard deviations, the probability of your data being included is pretty low. Or the probability that your data should be included based off of chance alone is pretty low. So that's kind of the way that we break everything down. And as mentioned before, the 2 standard deviation cutoff, or the rating of between a 2 and 3, is kind of where we set our goal for laboratories to be. We want to see as many of you as possible be inside the 5, 4, and 3 range. 2s do happen, it's possible, and it's going to happen to everybody sooner or later. Things like a sieve analysis, 1 or 2 stones happen to break apart or fall through, and it could throw you out. That's the reason why the accreditation program has some different requirements when it comes to taking action on the accreditation. We basically give the laboratories an opportunity to make the improvement and show that the corrective action was effective. So that's why the accreditation program does not suspend with an immediate low rating. The suspension criteria for the accreditation program is 2 consecutive rounds. So 4 samples where low ratings have occurred. Okay, the next thing I want to focus on is actually performing that calculation for the z-score and the ratings. And I think this is going to address that question that we had in the chat box, Kim. So here's the calculation. It's the lab value and the grand average. You subtract the grand average from the lab value, and then you divide it by the standard deviation, and that gives you your z-score. Okay, so if we do that math in this situation for this aggregate sample 205, 2.596 minus 2.6035 divided by that standard deviation gives you a z-score of minus 1.23. And going back to that bell curve and an explanation of how the standard deviation, how the z-score determines the rating, that z-score is beyond one standard deviation, but within a standard deviation and a half. So that gives us a rating of a -4, as you can see on that data sheet. Okay, I want everybody to just take a moment and make sure that they see that calculation, and that's where that comes from. And at any time, if you want to verify or double check, if you ever order a sample for training purposes, you know the sample, this is the way to find that information. And if you wanted to calculate your own rating for a training sample, this is exactly what you do. The laboratory data would just be, training sample A's result for, this specific criteria, oven dry density for, BSG. So, any sample that you get for training, like I said, you could calculate this out. If anything looks really weird when you see a rating sheet, you want to make sure things are correct, you can do this calculation on your own. And that's it's perfect. That's what we want. We want you to be able to go ahead and perform this calculation and make sure that you understand the way that it's derived and the way that it's developed. So here's the end of this next little section. Like I said, trying to just make ourselves take some breaks in between wherever we feel that questions may come up. So Kim, how are we doing here with the chat?
We have some questions.
Perfect.
So Jimmy wants to know, how do we determine the true value? And I'm not quite sure what he means with that, but hopefully you do.
So the true value, or what we define as the true value through our statistics program, is the consensus values from the participants. So is there a true reference value? And I'm going to answer that we don't have the true reference value. We use the consensus value from all of the laboratories that did the testing to determine what that quote unquote true value is, which what we hope is the grand average. Do we have one expert laboratory where we, have said, hey, no matter what, this is the actual number? And the answer is no. We don't feel that that's appropriate because that laboratory may have some sort of bias with a piece of equipment or a technician, or they may not be doing the standard, performing the test in perfect accordance with the standard. So there are variables out there, and we feel that when the analysis program was developed back in 2007, 2006, this was the most appropriate method that we could use to determine what the quote unquote true value is.
All right. Follow up, I believe, to this is, and you may have answered it already, about how you consider any outliers in that. I think you covered that, but is there anything else you want to expand on how outliers fit into the ratings?
Yeah, I can touch on that. A little bit. Like I said, that is essentially a whole nother presentation. It's something that we could definitely do, and I think that we might want to save that, Kim, as a target for next year, to kind of look and take a quote unquote deeper dive into the PSP statistics. So the way that the invalid and outliers are removed, when we look at that whole data set, once the round closes, all the data comes in, we take a look at the median. We actually do not use the mean. We look at the median first, and we take the median and determine what data falls outside of so many standard deviations. And I believe I have to double check on the specific number. I think it's 4.725 standard deviations. So if your data falls outside of that, when we just look at the mean median values, and it's based off of the percentiles of data, that is how we make the first cut. Then the second cut that we use is based off of I think it's 2.77 standard deviations. So like I said, that we can go into it. I would prefer to, like I said, save it for a whole nother presentation, because it would be too much to go into to explain how it was derived at this point. But that's basically it. We have a set value for what we determine as invalid outlying data, and it's based off of the criteria for how many standard deviations your data falls away from the mean when we're looking at that statistical program. I guess it's median based, excuse me. There are other proficiency sample programs out there that when they are talking about doing this trimming of the analysis, they'll simply look at what the standard deviation looks like. So they'll go and say, okay, well, the standard deviation is so much that we, excuse me one second. Oh, the standard deviation, is essentially cut, if you want to call it that, or the data set is chopped and trimmed until the standard deviation appears to not change. So if your standard deviation on something like a sieve analysis is 2.4%, they'll take some data, remove a little bit on each of the tails, and it'll be 2 point whatever. And once it gets trimmed down to where that standard deviation stays consistent, that's what we're going to consider to be, or what another PT program may consider to be, the actual standard deviation and the quote unquote true data set. So it's a little bit different, but we felt that it was just better to identify a specific criteria for what constitutes invalid and outlying data.
All right, thank you, John. I think we can move on and have the next questions I think you're going to answer in the next section. So.
All right, sounds good. So the next section, we're going to talk about the within lab repeatability. And just to keep everybody in mind that this is a consistency statistic. Okay, all participants have this value calculated for them. And it's just simply a measure of the variation between the grand averages for both the odd and even samples compared to the variation between your data for the odd and even samples. So we are going to take a second here and go over the calculation. And here's what it looks like. So you can see that we're simply looking at differences. The Y lab minus X lab, that's simply the even and odd data from your laboratory, the difference generated by the two of those, compared to the difference for the grand averages for the odd and even samples. We're looking at the difference between those differences, if that's the easiest way to say it. Then we divide that number by the square root of 2. And that whole square root of 2 thing, once again, that's another deal with digging deeper in the statistics. And like I said, that would be another presentation that hopefully we can get to at some point. But once we calculate that, that is the repeatability value or repeatability data point that's assigned to your laboratory. So once we assign that value, then we go back through the statistics that we went through with the within lab. So we'll go back in and we'll, or excuse me, the between lab, and we'll calculate what the standard deviation is for all those data points, what the z-score is, and what the rating is. One question we do kind of get is, how come there isn't an average? Well, the average should be really close to 0. So technically, if you have samples that are identical, which we try to do our best to have the samples be similar, but not necessarily perfectly identical, we would have the difference between the averages being 0. So then you would simply see a pure repeatability between your data. However, with the samples being slightly different, which is the intention of the program, we do account for that by calculating the difference between the two averages. So like I said, we simply take that value and we go through. Here's the data that we use, and we calculate it. So moving on to the next slide, this is going to show us how we actually do that calculation. And there's the numbers for that repeatability data point. Pretty easy. It's not incredibly difficult to calculate. And then we had to divide it by that standard deviation that we determined through the analysis, and we get our z-score, and you can see of minus 0.26, and that coincides with the lab rating of a -5. And I'm just going to give, like I said, give everybody a second here to look at that and make sure that we have an understanding of it. And if not, we can obviously address some questions as we move along. So the repeatability ratings themselves, like I had mentioned, it's a consistency statistic. We're going to go ahead and we're going to look at that stuff, over the course of time. How well are you performing it over and over and over again? So obviously we want to see high ratings. High ratings means that your laboratory has good consistency. And we would also note that low ratings would indicate that your laboratory has poor consistency. So the next slide is going to kind of be a little bit of a, wow, how is this possible? So we got to say, hang on a second, you got to take a look at this. You can have good sample ratings, but you can have a poor within value. And you can also have bad sample ratings with a good within value. And like I said, it's a measure of consistency. And this is one of the common questions we get. Well, how can that happen? And here are some examples of how that happens. You can see here in the top portion of this data, this is for an asphalt binder test. We have a laboratory that received ratings of -2 for both the odd and the even data sets. But their repeatability rating is a -5. And like I said, it's a measure of consistency. So you can see how in this case, they're very consistent, but there's something consistently wrong. And you can look at this, the lower portion here, where you've got a laboratory who has 2 ratings of a 5, a +5 and a -5, which are great. However, the repeatability or your consistency value is pretty low. And that just simply has to do with where your data falls about the average. If you look at that bottom case, you can see the z-score for sample 231 is 0.41. So it's on the high side of the average. And the z-score for sample 232 is at -0.9. So it's on the low side of the average. And being that 0.9 is very close to 1, it's pretty far out there when you're talking about the distribution. So that's why you see that low rating for the repeatability. They're on opposite sides of the distribution, and they're pretty far apart. Now if they're obviously +0.1 and -0.1, you're going to more than likely have a 4 or 5 for your repeatability rating. But as you move further away, even if you're in that range of a 5, you could still end up with a low repeatability rating. So the one thing that we have done to address some of the issues here is, if you note, the accreditation program does not take action on laboratories for low repeatability ratings. And it's just that simple scenario in the bottom half of this data set that you see. Laboratories doing perfectly fine. There's just some sort of measurement issue with consistency. And in the top portion, I think we can all agree that the -2s are way more something to worry about than the consistency rating. At least, like I said, you're doing something consistently wrong, or there's something consistently wrong with what's going on. So that's kind of the intent of the repeatability, is to try to look and see if there is any issue with your measurements. So I think with that, I'll go ahead, and I got another question slide up here. So do we have anything out there from this repeatability and reproducibility portion?
We do. So Peter would like to know, where did you get the S1 for the 0.0026 in the calculations?
Let's see, I don't know if I should go back, but on this slide, I'm assuming the 0.026.
I'm also assuming that, nope, it was there was more zeros.
I believe it's the 1S for the within lab.
Oh, thank you. Thank you.
The 1S for the within lab. Okay.
Yes.
Okay. So that 1S value, as I mentioned before, we have the repeatability value calculated for all the participants. That's something that happens on the back end in our data analysis. So once we have that data point assigned for your specific laboratory, we're going to take that value and look at that value and collect all of those individual points from every single other laboratory who submits paired data. And that's where that value comes from. We'll collect all of that data and assign the standard deviation to it based off of normal distribution and the normal statistics. Like I said, this is where, like I said, I could completely diverge into a whole separate separate presentation. I think it's something that we're going to need to consider doing and moving forward. This presentation is not at that level, but absolutely, I think we need to investigate that, Kim.
Why, thank you. And I think the next couple questions may be answered later in your presentation, and because they don't seem specific towards repeatability. So we'll move on for right now.
Okay. All right. Sounds good. So the next portion that we're going to talk about, we're actually going to talk about the Uden plot itself. And the name Uden, or kind of most people shied off scatter plot, however you want to call it. But the individual who is credited with it is William John Uden, and he's born in Australia. He came to the U.S. when he was a young boy. He's got various degrees in engineering and doctorates in chemistry. He did a lot of his core work is actually with a plant research institute, and he did some other information, some work with bombing operations in World War II, and he was at the National Bureau of Standards, which we all know now as NIST, or may not know as NIST, and that's where AASHTO Resource used to work. We were on the office on the campus of NIST up until about 7 years ago. So some of the stuff that Mr. Uden did, was on the grounds of NIST, where we once were. In his plant research, he actually did something kind of neat. I read a NIST paper that he had drafted, and I think it was in the 1950s. And all he simply did was have his students measure plant height for the same species of plant. They grew them in a greenhouse, and while measuring them, they decided to just spread them out across the floor. And then they got up on a ladder and took a picture of it. And shouldn't be any surprise, but when they took the picture, the plants were in a perfect bell shape. So it was evidence of, quote unquote, the normal distribution in nature, if you want to call it that. So that's kind of the background of where his stuff came from. Here's an example of the scatter plot. You can see them when you go to your ratings page. In the upper left-hand corner there, you can see the ellipse that we have where we circled where you can find it. And you obviously will receive a Uden plot, scatter diagram, for every single test parameter that's in the scheme. If you submit data for it, it's there. If you don't submit data for it, you don't have access to it. However, you can still go through and see what the scatter plot would look like if you were to go to our general data, general sample round analysis data. So it's there for you to see at any time. It's just a matter of how far you want to dig to go and get it. For your laboratory view, you can see we have the red dot feature and functionality there, where the red dot will pop up to show you exactly where your laboratory is at. It gives you the list of the outlying laboratories and then just the general statistics that come with the sample analysis itself. So then the other thing I really want to spend a little bit of time on today is the performance charts. And this is probably one of the most, if not the most important thing that we're going to share with you today. Oh, it disappeared. And the performance charts are incredibly critical when it comes to evaluating your laboratory over the course of time. To find those, it's simply in another link that's just right next to the Uden diagram selection in your data sheet. Once again, same thing. It's for any round that you submitted data for. We're going to collect and we're going to hold on to that information. So here's an example of what it includes. This data set that you see here is for Proctor. It includes about 10 rounds of data. So if you have more than 10 rounds, it's going to truncate it at 10 rounds. If you have less than 10 rounds of data, it'll just be for whatever you've submitted data for. If for some reason you did not submit data, you would see a dashed line go through that specific round. It would go from top to bottom to indicate that no data was submitted. Or if there was suppressed data, if there was some reason for us to suppress the data due to a bimodal distribution, or we had some sort of a sample error in production and we had to suppress the ratings for all laboratories, you would see something like that. But typically you see the data bouncing up and down right around hopefully the average. You can see that it's got paired data, it's got the reproducibility data and the repeatability data. And to kind of expand on that a little bit more, the repeatability data is just specifically the 2 points that are under each round. You can see on the bottom of the table here, on the bottom of the graph, we have the sample rounds, in this case 157, 158, all the way through soil rounds 171 and 172. The circle and the square correspond with the odd and even data points for the repeatability. And the distance between those two data points is the reproducibility. So basically, the further those 2 points are away from each other, the lower the reproducibility score would be. So what you really want to see in your in your performance chart is the values just above and below that red z-score of a 0 line, and the 2 points be very close together. You do not want to see a lot of separation between the two, because that would indicate a within lab error. This really allows you to focus on single point isolated events or recurring issues. And I think this next little slide here or this picture that I showed or slid in shows you where, you know, a reoccurring issue is taking place with a specific laboratory, and you can kind of actually isolate where it took place. If you look, you can see somewhere around sample 19 and 20, hopefully it's clear enough for y'all to take a look at it. You can see we started to drift away with this specific parameter, and that's the total material passing the 100 in a sieve analysis. And you can see that the data started to push away for a specific reason. Now, the laboratory's data was still inside of 2 standard deviations on the z-score. So they were still okay. The lab was getting, you know, 3s, and everything appeared to be okay. And then all of a sudden it shot up again right around sample 27 and 28. So you could see that there was an issue going on at some point, and it actually transpired back, I mean, roughly you're looking at 5 years. You know, you get back to around 19 and 20, that's where this initially took place. But you can see that whatever was going on was kind of trickling its way up to cause a problem, and really became apparent with around 27 and 28. So this is, like I said, one of the most important things and important tools that you have in your quote unquote PSP toolbox to make sure that you understand what's going on with your data and how well your laboratory is doing testing. So like I said, please keep this in mind. It's by far one of the most important things that we have out there to offer to all of you. So I think with that, Kim, I think we're looking into some other information that we have here. We've got some newsletter articles for low ratings and how being average has never been so good, what happens when you get a low score, and a little bit of a discussion on precision and accuracy. If anybody's really interested in that, you know, good reading material when you run into something. We'll continue on here. Like I said, I wanted to try to do our best to make sure we had quite a bit of time to have discussion. So just to kind of recap what we talked about, we just did a very brief overview on where to find the reports on the website, the distribution of the data and the ratings associated with the distribution. And then we took a look at some calculations for z-scores with ratings and repeatability, single point and continual performance by use of the Uden plots and the performance charts. So hopefully we kind of hit all those initial learning objectives, and I feel that we did. Hopefully everybody got something out of it, and I'm going to move on to the next slide. And like I said, the intent is to just make sure that we get a lot of questions, and we do our best to answer as much as we can today with this this roughly 45 minute to an hour window we got. So how are we looking on that chat box?
We're looking pretty good. Again, keep your questions coming in. We have about 15 more minutes or so of this, so we have plenty of time for some questions. Robert wants to know the S1 value can only be calculated by AASHTO, correct?
It's specifically calculated by the analysis that was approved by AASHTO Resources Oversight Group. So if you ever want the research paper, that was derived from, it's an NCHRP study. It's 9-26 phase 3. You can, I think it's actually free to download, I believe it is. But you can get a copy, and it gives you the detailed review of the analysis. But yes, the the standard deviation and the way that it's derived and calculated was specifically approved by now AASHTO Resources Oversight Group.
Thank you. And Valerie would like to know if there's a reason why we convert to ratings instead of just using the Z-scores.
I think that's just a typical thing that PT providers do. It just seems to make it easier for laboratories and people to understand that, well, a 5 is a good rating and a 0 is a poor rating, rather than have someone go and say, okay, well, my Z-score is a 1.73, that's good or bad. So, I think we just assigned the ratings to make it easier. We're looking at trying to do some other things with IT solutions to give a better representation of where your data is and how your scores appear. So that's one thing you hopefully will see coming down the road. But that's it. It's just simply a way to hopefully make it easier for people to understand where they sit.
All right. Now we have some questions now relating to accreditation and the proficiency sample program. So we'll go on that vein for a little bit. If a laboratory has a low rating and we request another sample to redo the test and we get another low rating, what would that result in?
It depends on if the initial low rating was the result of a suspension or resulted from or result in a suspension, I guess is the way to say it. So if you receive a low rating, say a 0 or a 1, you're not going to be suspended for that first year per se. If the next following year, the next following sample, you receive a 0 or a 1 on that same exact line item, that same test parameter, say the number 8 sieve in whatever sieve analysis, that's where you would get suspended. If you were to receive a low rating at, say this current course aggregate sample that's out there now, if you were to get a low rating on one of those sieve sizes on one of the samples and you called us and said, hey, can we get another sample just to check for training purposes? And, we're going to do it on our own. If there's another low rating that's basically you just doing investigation, that's just on you to do the investigation and follow through with it. We're not going to take any action on a sample that you purchased outside of the scope for any kind of training or rectification if it's not involving the accreditation. Like I said, if it's involving the accreditation and your laboratory is suspended for PSP, you would call us or email us or however, you would get in contact. You'd order an extra sample. It would be blind, so you wouldn't know, any data within the sample. You would just simply know that it's a sample, and we would provide the instructions to you. You would test it. If that data that you receive from the blind sample is low, the laboratory would remain suspended. They would not be reinstated for that specific method. But that's kind of what it comes down to. It's a difference as to whether it's an accreditation decision or whether it's just a simple corrective action opportunity for the laboratory to figure out what's going on.
All right. I think you answered 2 questions there in that response. So thank you for that. Somebody else wants to know, how important is repeatability to laboratory accreditation?
Okay, so the answer within lab repeatability, I promise I can say it. It's important to the extent of that consistency that we were talking about. When it comes to actual, action on your accreditation and suspension and revocation, it's really not important when it comes to that criteria. But when we're talking about evaluation of your individual lab ratings, then yes, it's extremely important, because that's an identifier of a possible issue. And that's why we point out the performance charts. And that's why we point out the measurement of the consistency and try to make it apparent that, you obviously want to see 5s across the board. And if you see, 2 2s and a 5, like we showed in that example, then there's something more that you need to look into, and you need to take a little bit more action, even though the ratings don't warrant a suspension. So there's merit to it. The accreditation program just does not act on it. However, it should be part of your investigation whenever there is an issue with either the accreditation itself or when you receive a low rating.
All right. Thank you. Jody wants to know, is it better to have different analysis? Sorry, yeah. Sorry. My cat was distracting me. I apologize. Is it better to have different analysis and use different equipment, et cetera, to analyze the different samples, or should we control the variables within our lab when you're testing the samples?
So if we are going to try to determine within lab repeatability, it needs to be, the sample should be tested in the shortest window as possible between the two, using the same equipment, using the same technician, hopefully under the same circumstances. We really do not want to have, in our case, I wouldn't want to see myself test sample A and Ryan test sample B. You would want to make sure that the technician is testing, basically if you're looking at the data sheet, you want to see that the technician tested across the row, not up and down the column. You want to make sure that an individual completed both sample A and B for that specific parameter. We don't want to see them split up, because at that point, you've already got a possibly gigantic variable of having another technician run the test. So everything should be conducted on the same equipment with the same technician. And that's, like I said, test specific. If you want to have, Kim can go in and run the wash portion of a gradation. Maybe you don't want Kim to do that, I don't know. But then Ryan could go run the gradation component of it, the sieve analysis, and then I would take that material and then I could go and run another test on it. But it basically needs to be separate tests, not anything in between.
Thank you for that. And you definitely don't want me running any tests. Not my strong suit at all. Peter would like to know, what % of error could be contributed to our sample preparation for proficiency samples? So how much of it could be our fault in the production of it?
So we try, obviously, we've been trying our best for years to make sure that the samples are as homogeneous and as stable as possible. Ryan, you can chime in on any point here on how much testing you do to make sure that the samples are as reasonable as they can be to go out the door. So I'm going to give you a few seconds here. I've been talking for about 50 minutes now. I think it's time for you to jump in here and explain what kind of testing you do to make sure the materials are good.
Sure. I mean, it's my entire job is to make sure that our samples are as homogeneous and as stable as possible. So we're not necessarily running the full suite of tests that you guys are. We're running something that looks at the product. For aggregate, for example, we're doing gradations. And we're trying to make sure that those are as consistent as possible. And that's also kind of why we go with the grand average for our result, not a number that we're giving you, to account for that little bit of variability.
Yeah, so to kind of piggyback on what Ryan said, basically our accreditation for ISO 17043 requires Ryan's job essentially, and he grinds away back in the lab as soon as we prepare samples, and we collect the data. We take split samples from every round, and he runs a bunch of tests. Specifically, I think it's 2 subsamples per sample for 10 samples that we randomly pull from our production line. And then we do analysis of variance on it, make sure that it's meeting that criteria. We also take a look at the data that Ryan generates, compare it to the precision estimates in the standards. And I know that's always a big question. Why don't you guys use the precision estimates in the standards? We're looking at a single point performance issue. We're not looking at the whole world of aggregates and what the summation of all the variability can be. And the other thing is, while we do use the precision estimates in the standards, our criteria is actually set that we try to stay to be within 33% of that limit. So we really kind of cut ourselves down with and try to be as accurate as we can and provide the good material that we try to provide. When it comes to just the samples before they go out the door. And beyond that, our equipment is calibrated by an ISO 17025 calibration agency. when we're processing our coarse aggregate samples, the sample crew, as the material is coming out of our large sieve shakers and dropping into the drums that we use, they're pulling, I think it's between 30 and 50 subsamples between each split of shake that they do. They take that material and they run it on a Marianne with 12-inch sieves, and we try to stay or make sure that that material is either less than 1% passing on average or below 2 standard deviations. So we really try to do a lot to make sure that the material is as good as possible. I won't say it's not perfect. There are times where we've weighed material out and things happen. A balance cord hits the edge of the pan for 50 samples, and the data comes back and you just see a clump in the Uden plot, and it's like, oh, what happened. So at that point, we just suppress the round. And I think, let me see here, I think it's part of the thing, and I'm kind of jumping ahead, but this picture here on the left, this is a notorious dump day for a coarse ag sample. We load the material into our hoppers and we weigh the material to specific gram amounts in the boxes for the coarse ag samples that you guys have. And we had one of our engineering technicians inadvertently put a 3/8 inch drum of material in the 1/2 inch hopper. Fortunately, we caught it during the homogeneity testing, so none of the laboratories received any of those samples, but it forced us to throw out 600 samples. It took another day and a half to sieve the material back so we had enough of what we needed, and then we had to start the production back up again for packaging. So as much as I want to say it doesn't happen, it does. And we just do our best to make sure that it never makes it to any of you. And if it does make it to any of you, we always will suppress the rating to make sure it doesn't affect your accreditation. So that's kind of what happens if things do go wrong.
I want to say we also have some videos on our YouTube channel and on our website about to see some of the production of some of our samples. So if you're interested in any of that, we have a couple of videos up there. They're a little old now, but to get an idea of how we prepare our samples. And I'm very shocked that we have no more questions. So if anyone have any more questions, feel free to type them in now. But right now we have no questions waiting. So give a second. Well, a full minute would be torture.
Minute of awkward silence.
Torture if we were just sitting here for a full minute waiting for questions to come in. But seeing no spike in the questions, maybe we do have some. Do you do any correlation between sample A and sample B?
I'm not necessarily sure what is meant by correlation. I mean, the Uden plot is the correlation between the two samples. That just simply shows how they're related and how different they really are. When you look at the repeatability measurement and you look at the Uden plot, that 45-degree line that runs right through the center of the Uden plot, that is the measure of the repeatability and where that line stands. So in essence, the closer that line is to a perfect 45-degree line, the more identical the samples are. And like I said, our intention is that the samples need to be extremely close, but not necessarily perfectly identical. So usually that 45-degree line, it's almost smack dab at 45 degrees every single time. There will be some rare instances where it is off a little bit. And to be honest, I don't think that we have ever had our samples off far enough to make a significant effect between the two. We also take a look at the standard deviations between every round. That's part of our analysis. So, in this example, or an example that we have out right now, I think CoreSag 209 and 210 is out. I can't remember what the numbers are anymore. It's all running together. But we'll look at the analysis from this round and we'll compare it to last year and the year before and take a look and see how things compare. Usually the standard deviations between the samples are very, very similar. we typically do not see any kind of major shift between A sample and B sample, even, odd, whatever you want to call it.
All right, thank you. And one last question. Were there any anomalies with this year's fine aggregate number 30 sieve?
I would have to go and specifically look at that data. So whoever sent that, if you could please send me an email, that would be great. We have some contact information here. I think that's a pretty good segue, Kim. What do you think?
I think so too. Yeah, I thought that might be too specific. I thought I'd just throw it out there.
Well, we can always go back to questions, but here's some information that we have out there. You can always email info@ashtoresource.org for any kind of emailing. My specific contact information is here. We also have the general proficiency sample program email account, which is psp@ashtoresource.org. So please, whoever asked that question, I'll gladly take a look at it and see what was there. So,
well, thank you very much, John. Thank you, everybody, for attending today's webinar and asking questions. And again, feel free to reach out to John or Ryan if you have any specific questions, and we'll be happy to answer those. Our next upcoming event in the webinar series is in November 19th. And there's the information there. So if you haven't registered for that, please do. And as you leave the webinar session today, you will be prompted to fill out a survey. So please feel free to give us all of your honest feedback on today's session, and that will be very helpful. So thank you, everybody, for joining us. Thank you, John, for taking time to give us very detailed answers to all of those great questions. Have a good day, everyone.
Kim, I appreciate it.
Have a good day, everyone.